Οκ, από μένα.
Οκ, έλα. Κώστα, λοιπόν, να καλωσορίσουμε... είμαστε όλοι από Ελλάδα, από ό,τι βλέπω. Κώστα, σε ευχαριστούμε που είσαι εδώ και σήμερα και συνεχίζεις με τη δεύτερη, με το part 2, έτσι.
Εγώ σας ευχαριστώ για την πρόσκληση. Να δώσω την ομιλία στα ελληνικά ή στα αγγλικά, αφού είμαστε...
Ό,τι σου είναι πιο εύκολο, Κώστα. Βλέπω ότι είμαστε...
Θα τη δώσω στα αγγλικά για να υπάρχει και συνέχεια, αφού είναι
ωραία,
και οι δύο
ωραία,
ηχογραφημένες.
Ωραία.
So, hello everybody and welcome to the second part of my talk. Today we will first recall some things from last time. So, I recall from the first talk that affine Hecke algebras are certain deformations over a parameter Q of group algebras of Coxeter groups. The fact that they have a large center, and that we want to prove a conjecture stating that the reducibility locus, which is a closed subscheme of the central characters inducing a reducible representation, deforms flatly with respect to Q. So if you recall, the center for these algebras was some torus Mundeville group. Every central character corresponds to a point in this variety. And if we look at xt being the set of characters who induce a reducible representation, that locus should deform flatly as we change the parameter. So with that, let me move to general ideas of the talk. So let H be a non-commutative algebra that is a finite module over a center that is itself a finitely generated K algebra. In particular, it can be any kind of Hecke algebra. You take K to be C, and then basically any kind of Hecke algebra has this property. Affine Hecke algebras, double affine Hecke algebras, Serednik algebras. In the case of Serednik algebras, you do need to take T equals 0. So today we will show that the reducible representations of H can be identified with the K points of an open-dense subscheme of an affine scheme, which that affine scheme we will call it the Lafforgue variety. This has to do with the fact that the existence of this object was first proposed by Laurent Lafforgue. In some notes I've added to the references. And I'll first begin by showing this construction. We will study the geometry of the Lafforgue variety, and then we will show that at least under appropriate assumptions, so for this talk, basically the center being regular, the Lafforgue variety varies flatly under deformation. This allows us to prove the conjecture when the same assumptions are satisfied, because it will turn out that the Lafforgue variety can detect the reducibility locus. Without further ado, let me start with the Lafforgue variety part. So let A be a subalgebra of the center. We assume the following, and it's enough to assume it for the center, that A is a finitely generated K algebra and that H is a finite A module. For this construction to work as it is, we also need the characteristic to be 0. And you can also safely assume K is algebraically closed for the start. So if we take any element in H, we can define a function from the reducible representations to K bar corresponding a representation to the trace of H at V. Basically, we look at the trace function, but we look at it as a function over the representations, not over the elements. So we look at all maps from the reducible representations to K bar, and we consider the subring generated by these specific functions. Now, as an example, if H is itself commutative, the trace ring will just turn out to be H. All the reducible representations will be characters, and this will just turn out giving us back H. Why did we define this trace ring? Because we want to take a spectrum. This Lafforgue variety that we considered that we are going to be talking about is basically going to be the spectrum of this trace ring. So in the commutative case, it's just a spectrum. So Laurent Lafforgue claimed the following, and this will basically be our main theorem. He didn't exactly claim the whole of this, but so we define the Lafforgue variety to be the spectrum. Claim there is an open-dense subscheme of this Lafforgue variety such that the natural map given by the factor of points, so if you were here last time, remember that we look at affine schemes through the factor of points. So to give a point in the spectrum is the same as giving a homomorphism from the ring of functions to K bar. And we just consider the function given by evaluation. This gives us a way to send irreducible representations to this affine scheme at least. And we claim that this induces a bijection with the geometric points of an open-dense subscheme. We also claim this was not part of what Lafforgue proposed, but we also claim that the natural projection you get from the Lafforgue variety to spec A. So if you recall, this is the center. Basically, what we're talking about is taking the central character here. So if we have a point here that is a module, we can look at the central character, and this character will be a point of spec A, considering spec A as homomorphisms. So as an example, recall from last time the case of an Hecke algebra for GL2F. So F here is a local non-Archimedean field. The only thing we basically care about is that this Q is the cardinality of the residue. Now, we made an argument like this last time when we want to classify the simple modules here. If we take a V to be a simple module and small v an R eigenvector, these two vectors generate the whole representation. Why? Because this is a simple module. Every other element of V can be written as HV for some H. And by these two relations, any H can be written as R1 plus TSR2. Because there are no TS squared, we can remove them all using this equation. And then if we have elements on the left-hand side, we can pass them on the right-hand side, plus an error there. So we can write everything in this form, and that means every HV is going to be some scalar coming from here times V plus some scalar coming from here times TSV. That means there are only three cases. Our simple module can either be two-dimensional, and in that case, there's a specific module which we can concretely describe using these relations. We can just look at it using this basis. And it provides us a unique module as long as we specify the value of x and the value of y, essentially. Then there is the case that our simple representation is one-dimensional. And in this case, TS only has two choices. It needs to have a scalar because the representation is one-dimensional. It can either be -1 or q. The trace ring we get, in this case, I've written it down. You can see this because basically any central character will give us a modulus in 1. And this is where this factor comes from. And here we need restrictions. For the module to be one-dimensional, we need to restrict. Basically, we need x is equal to qy or y equals to qx. This is similar to what we saw last time. So we get two other components that look like this. And the center, we know, is the W invariance. So using this computation, we can actually, for this case, we can just draw the Lafforgue variety. It will turn out to be something like this. So this component comes from the induced representations, and these come from character and Steinberg representations. The natural projection is just taking the central character. I want to also remark that if you specify central character, we can see the reducibility locus here, because if we look at it on spec of A, then the reducibility locus is exactly when this projection is not one-to-one. So you only need to see when this projection is not one-to-one. So before we pass on to more properties of this object, let me give you excuse me, I have a problem. Sorry, my tablet disconnected. Okay. Before we pass to the properties of this object, I would like to present the proof of our main theorem. So what we'll need are some auxiliary objects, which are basically a non-commutative version of the Hilbert scheme. We define the non-commutative Hilbert and nested non-commutative Hilbert functors as functors from commutative rings over A to sets given by these formulas. So when I say up to equivalence here, what I mean is the obvious notion if we're given two different surjective morphisms like that, we require then is an isomorphism that respects the diagram. And the nested non-commutative Hilbert functor is the same. We just have another surjection here. And we also assume this surjection is honest. It's not just an isomorphism. And we require from all modules to be flat over B, to be flat as B modules. What we want is the following proposition. We want to show that these functors are representable by proper schemes over spec of A, because their auxiliary objects will use to construct the Lafforgue variety.
Sorry,
How
Kostas,
we'll do it?
Can you
Yes?
repeat what is M and N?
M and N are H tensor B modules. So these are all sequences of H tensor B modules.
Okay.
And the only requirement is that M and N are flat as B modules.
No restriction on the finite dimension.
No, but this will come naturally from the fact that H is finite is a finite module over A.
Okay.
At least for the reducible modules. So we want to show these functors are representable, and what we'll use is the quad scheme we saw last time. Let me review that. So this is the definition of a family of quotients, as we saw last time, of a sieve. And let me this time explain what happens if we make the very simplifying assumption that both of these schemes are spec of A. In that case, then E is a coherent sieve on X. Well, X is just spec A. That means E is basically, we can transport these two. E is basically an A module. So for the map from T to S, I'll also assume T is affine, and I'll denote this by spec B. So a map from spec B to spec A is the same as giving a map from A to B. Then a family of quotients of E, which we correspond to the A module H, is a pair of a coherent sheaf on X tensor, on X fiber product with T. So in particular, in this case, X and S are the same. So on spec B, and that makes F a B module, which I'll denote by M, such that the support of F is proper over T. This assumption for affine schemes is null, and F is flat, which means F flat as a B module. And we also need the surjective homomorphism, which, following the definitions, will just be this. Because it is this pullback, which in the affine world will just give us a tensor product. So you may remember from last slide seeing the exact same thing. That is not, of course, a coincidence. So we recall that this functor is representable from last time, the quad functor. And now we can prove the representability of our non-commutative Hilbert schemes. So let X be spec of A, as before, F a coherent sheaf on F the coherent sheaf corresponding to the A module B. We claim that our functor is a closed subfunctor of this quad scheme. And indeed, we just saw both functors are of this form. The only subtle difference is that in the quad functor, we look at all this as B modules, where in our Hilbert functor, we look at this as H tensor B modules. But asking from a B module to be an H tensor B module, that's satisfying some infinite set of equations, which will give you a closed subfunctor. So that's what I mean by this sentence. And when you have a closed subfunctor of a representable functor, it also has to be representable. In particular, because the quad functor is representable by a proper scheme, and this is a closed subscheme, it will also be proper. And the proof for the nested Hilbert scheme is very similar. Any questions on the representability of the Hilbert functors?
So Kostas, so can you say a bit, so what is the reason for considering this particular property?
The reason for this particular property is that I want to use it in the next part. Which one of the properties?
That is representable.
We need it because we basically want to work with a scheme. So this will be an auxiliary object we want to use to construct the Lafforgue variety. So we need it to be actually a proper scheme.
Okay, I see. Okay, thanks. Yeah.
And you can view it as indeed, it's a non-commutative generalization of the classical Hilbert scheme. If you put H to be commutative, you will get back the classical definition.
Okay. Thanks.
So now that we have these non-commutative Hilbert schemes, let us also define this affine scheme. By the symmetric algebra, I mean tensor products like that. And we consider the following maps. Fn from the nested Hilbert scheme to the Hilbert scheme just forgets n. And the trace takes a module and sends it essentially to the trace function. This is exactly what the... Sorry, I have some problems. I have some technical problems with a laptop and it doesn't work. With a tablet and it doesn't work. You can write again. Okay. So Fn is just a factor that it's just a map that forgets n. Remember that the nested Hilbert scheme has some nested sequence of modules. And ignoring this one, it will give us a point in Hilbert. And the trace map sends a module to the trace function generated by it. So in particular, you can see that the image of this map essentially will have ring of functions th. And both maps are equivariant with respect to the invertible elements.
Sorry, Costa, when you take the symmetric algebra, you mean H, you view it just as a finite module over A?
Yes.
So it's just polynomial ring with coefficients in A generated by the basis of, or the dual basis of H or something.
Exactly.
And then V is that projective space. Ah, no, affine space.
V is an affine space, and that will play that will play a role in the next slide. So thank you for the observation. Yes, basically we want essentially a context in which we can look at all the functions generated by the traces. Because a priori, not all functions corresponding to traces come from some FH itself. When you add two traces, you'll get another trace. But when you multiply two traces, you get an honest new function sometimes. So this is the reason for considering the whole symmetric algebra, and not just everything coming from H, to get the whole trace ring as the image of this map. So we put these maps in a sequence of maps of schemes. Here, we recall that in the nested Hilbert scheme, we have modules like this, we parameterize modules like this. And in the Hilbert scheme, we parameterize modules like this. We set the Lafforgue variety to be the image of the trace, so it will be spec of th as before. And the open-end subscheme, we define it as being the complement of the image of the composition. Why does this object indeed parameterize simple modules? Well, if something is in the Lafforgue variety, it means it comes from somewhere in the Hilbert scheme, so it comes from a module. On the other hand, we need it to not come from the nested Hilbert scheme. So what are modules that live in here? They are modules that do not admit any subquotient. If they did, they would come from the nested Hilbert scheme. So that means they are simple. It means when you remove this composition, you just keep the simple module.
So, Kostas, subquotient from where?
From M.
From M, okay.
So if M here is a simple module, that means it cannot come from the nested Hilbert scheme, and vice versa. If something comes from the nested Hilbert scheme, it couldn't be a simple module to begin with.
Okay, thanks. Okay.
And then we take this trace map here, which, what does it do? It gives us the actual honest modules up to equivalence, because if you are a little careful, you'll notice this doesn't parameterize exactly the modules themselves, but the modules together with a generator. Why together with a generator? Because you can take one here and look at where it goes. And this is a canonically defined generator. The trace map essentially geometrically forgets this choice of generator. It just keeps the data of the module. But there is something else important to see, because we really need this finiteness of P. Well, the Hilbert scheme is proper. That means its image, the Lafforgue variety, also has to be proper by general algebraic geometry. And that means the morphism P is proper by the definition of properness for schemes over spec of A. And it's also affine because, well, the whole V H over A is affine, and this image being proper is a closed subscheme, so it's also affine. So this morphism being both proper and affine, again, by classical algebraic geometry, it implies P is actually finite. Any questions on that? So what can we notice from this proof about the Lafforgue variety? Well, for one, as a scheme and not just as a set of points, it does not depend on the choice of subalgebra that we get, at least as long as it's an appropriate subalgebra. So we still need to have H being a finite module. The reason we want this is, as we saw last time, we sometimes want to take a regular subalgebra if Z is not already regular. Now, almost Morita equivalent algebras have isomorphic Lafforgue varieties and center compatible with the central character projections. Why is that? Because everything involved in the construction of the Lafforgue variety only depends on the category of representations, or in particular, the finite dimensional representations. And the converse is not true. You can already see this in, we'll already see this in the SL2 example at the end of this talk. We'll work everything out for SL2, and we'll see that even for very simple cases, having the same Lafforgue variety, even together with the centers. So a remark on this, if you want to have any reasonable notion of equivalence, you need to also assume the centers are equivalent. So you look at two algebras together with their centers. Together with the data of the projection, and you require a commutative diagram like this. Otherwise, you can get very bad examples from just comparing the Lafforgue variety of a non-commutative algebra with the Lafforgue variety of the trace ring, which, by virtue of being the spectrum, the trace ring is commutative, will just be the same thing. But of course, they are not very similar. So you also want the data of the projection. And the last thing we'll also see afterwards is that the Lafforgue variety just turns out to be a union of irreducible components, which are closed subschemes of spec Z. So you can see this in this picture for GL2. Essentially, this is spec Z. It's the same. And these are isomorphic to the deformation locus, because their image here, they are isomorphic to their image, and it's just the reducibility locus. And if you take GL3, you'll just get a bigger picture that looks the same. You'll get some kind of cube and some hyperplanes corresponding to the reducibility loci, and then you'll get some even smaller subsets, which we will see later where they're coming from. But essentially, the largest dimension will just give you components isomorphic to spec Z, and then other dimensions will give you, the next to smaller dimension, the next to maximum dimension will give you the reducibility locus, and then there are other subsets. And that concludes the first part of the talk. In the second part, I want to talk about the particular conjecture we saw last time. So we recall the following. The affine Hecke algebra, which is defined from some root datum. In particular, this is just a Z lattice, has center which are regular functions on some GIT quotient of a torus by the Weyl group, and the torus is just the spectrum of the group algebra of the co-character lattice and W the Weyl group. So given an irreducible module with central character He, it has to be an irreducible subquotient of the induced representation, and this induced representation is generically reducible. So we define, if we look at this variety whose ring of functions is the center, again by the factor of points formalism, each point on this variety corresponds to the central character. And then we can induce this central character and ask if this question is, if this induction is irreducible. We let xt be the set of characters which do not give you an irreducible representation, that give you a reducible representation. For the algebra it's t when you specialize the parameter at t. So when you specialize the parameters at the parameter at different t's, you will get a different reducibility locus. And the conjecture states that there exists a flat deformation of schemes between x1 and x for the square root of q. So this is where the Lafforgue-Hecke algebra appears, and this just gives you a group algebra. That is something very concrete. Well, the Lafforgue-Hecke algebra is also very concrete, but the group algebra is even simpler to work with. We recall that this conjecture was also proven for the cases of GLN, SL2, and G2, but today we want to do something more general. And again, by Aubert, Baum and Plymen. So xt is just going to be a component of the Lafforgue variety of HT. If you consider in general a family of non-commutative algebras, and you don't really need to take C here, with center Z, and we assume Z is regular, we can prove the following theorem. That this map is actually a flat deformation. So if this is a flat deformation, we get that the whole Lafforgue variety varies flatly with Q. That means in particular, the reducibility locus that we're working with here also differs flatly over Q. And a natural question is, how much can this theorem be generalized? To answer this question, we will sketch the proof of this theorem. But before we go on with that, I can't remove the annotations. Okay, what I will do is close the tablet and just annotate from the computer. So, any questions on this part?
Kostas, can you elaborate a bit more? So what it means for this particular variety that this map is a flat deformation?
Is a flat deformation over Q, so that basically that this map is flat. You can forget the deformation. It's a deformation when you vary Q.
Okay. So it's
As last time, we consider this map not just as a map, but as a family of the fibers over the points of this. And as such a family, we claim it's flat.
Okay, yes, I see.
Thank you for the question. So, for I want to emphasize the fact that this is only proven in the case of a regular center. So it does not include all affine Hecke algebras. Not every affine Hecke algebra has a regular center. But for the cases where the center of this is actually regular, we have the conjecture. This includes the previously known cases, GLN, SL2, G2, and in general, it includes any affine Hecke algebra coming from a split adjoint group, for example. They all have regular center. So
sorry,
let me
can
now
I ask
assume.
also,
Yes.
The center varies within the family, or is it the center of the relative thing of the family?
So the center here does not vary over the family. It's always T mod W, but you don't need it to be constant for the theorem.
So it's not. So it's the center of each fiber, each Hecke algebra, not the center of HQ. The center of all, for all values of Q, they all have the same center. This is what you're saying.
Well, you could take they all have the same center. What you could do here is instead write, instead put Q in Z as well, because, well,
Okay.
the center of this algebra has to also involve Q.
Okay. Thank you.
So, but first to prove this theorem, we need to actually study this reducibility locus. So let me also assume H is locally free as a Z module, even though this, for the regular center case, and assuming H is Cohen-Macaulay, follows directly by miracle flatness. So if M is a simple H module, we recall that the projection sends a module to its central character He. We can see M now as an HE module instead of as an H module. And then we denote JHE, the Jacobson radical of HE, and we have the Artin-Wedderburn theorem telling us exactly what the semi-simplification is, where NH is the number of irreducible representations. And we also define the stress. So what we want to detect is this number NH, because if you recall this picture, and it's going to be horrible because I draw it from my laptop, but what can I do? Then this number is detected by P. It's going to be 1 outside the reducibility locus, and it's going to be 2 over the reducibility locus because there are 2 irreducible representations on the fiber. And there's a point on the Lafforgue variety that does not correspond to an actual simple module. It's a point that we remove when we take the open dense subscheme. But it does correspond to a module. It essentially corresponds to the induced module, but this module is not simple. So we have to remove it for the open dense subscheme. So this number NH, we can detect it from P, but we can also detect it from this trace form because, and I will not talk about this proof, it will change together with a Jacobson radical. So the only thing we have to detect is this Jacobson radical here. And we can detect it using this trace form. Why? Because if you see this as a function from H to H dual, and with that I mean linear homomorphs from H to A, then the Jacobson radical is the kernel of this trace form. So in particular, for the case of an affine Hecke algebra, this is generically trivial. An affine Hecke algebra is generically semi-simple. And this NH is generically 1. What's the only case it can increase? We need for some H to have an actual non-zero Jacobson radical. But we can detect this Jacobson radical as the kernel of this trace form. And this trace form, with H being locally free, we can locally write it as an n by n matrix. So you look at this as a module over, as a locally free module over A, and you look at it locally as a free module. This is also a free module that can be non-canonically identified with H. So you can write this locally as a matrix, and then you can just take the determinant to detect when the Jacobson radical is non-zero. We define this number to be the discriminant, this locally principal ideal to be the discriminant, and the definition is very similar to the classical case coming from numberings. And indeed, we also need a lemma similar to the numbering case, that if we have commutative algebras here, there is this formula. This for numberings is extremely classical. It's sometimes useful for us to do it for more general commutative algebras. This is not a difficult lemma. It's just useful when you change your basis. And it can be shown by looking at the color differentials. You can see more details in my preprint.
So n is norm.
N is the norm, yes.
The extension, but don't you want B to be free over A or something?
Locally free.
Okay.
Just locally free is enough. Okay. So you want everything to be a finite extension over the other thing, but in our in the cases we will see, because you already have a finiteness coming from H and everything will live there, everything we will see will be a finite.
Okay, so B over A is an extension of commutative things, so you can take it on. Okay, I see.
Yeah. So this discriminant now detects the reducibility locus, at least in the case where we're at, where the center is regular. This discriminant detects exactly the reducibility locus. If the center is not regular, you need to take a regular subalgebra and you lose something from your criterion. Because when you take a regular subalgebra of Z, this will correspond to a morphism from spec of Z to spec of A, and you need to work out to work outside the singularity locus of this morphism. But for the regular center, this discriminant exactly detects the reducible representation. So let us just do an example for GL2F. And by that, I mean the Lafforgue algebra of a GL2F. So we consider, to compute the trace form, we consider the basis of H over the Laurent polynomials, given by this element. This is a tweaking of TS such that it satisfies a semi-linear property. So instead of this complicated relation, it's just semi-linear. When you pass something from the one side of IS to the other, you just act by the value. The problem with that is this is actually not an honest element of H, but it's an honest element if you look at the fraction field, and at least for computations with discriminants, we can work over the fraction field. So we don't mind this is not an honest element of H, what we do care about is it's linearly related with TS. So nothing changes when we take the determinant. Why do we take these elements, which, if you're familiar with Hecke algebra theory, correspond to intertwiners? Because when we write the trace form as a matrix, we're going to get a particularly simple matrix. We're going to get something block diagonal. We're going to get something block diagonal because outside of the cases where we are in these blocks, then the eigenvalues, the eigenspaces are being permuted. And everything that permutes the eigenspaces is going to give a zero trace. So the trace form simplifies by a lot when we look at this particular element. And you may ask why these elements are being defined. These are being defined, essentially, these exist more generally for any split reductive group. And in the case of GL2, they are exactly these elements. So you can compute the discriminant of this just by hand. This will give you x plus y squared minus 2x squared plus y squared. As a computation, this will give something like x minus y squared. And we'll get something similar from the other block. These are going to cancel with the denominators here and leave only the EA, which is why we get this. Does this computation make sense? So the same computation works more generally, exactly in the way we saw. Well, there are technicalities, but you can use the same trick to compute the discriminant for any split adjoint group, and you'll get this. So for a split adjoint group, you get that the reducibility locus is exactly zeros coming from here. And this is the same result for split adjoint groups with the one of Shinichikato we saw last time. Now, instead of just considering the determinant, we want to also detect the other components of the Lafforgue variety. So what we can do is we consider II to be the determinantal ideal, the ideal generated by the minus. What does this do? It detects the rank of the Jacobson radical. The determinant just checks if the Jacobson radical is 0 or not 0. But these determinantal ideals also check what is the rank. So we define this stratification to be the Jacobson stratification of spec A. What is going on? In particular, if you look at this example again, well, then you only get the discriminant, and y1 will turn out to be the reducibility locus. Of course, if you look at GL3, then you can continue taking the Jacob stratification and get Sapler loci. So the components of the Lafforgue variety all end up being isomorphic to some stratum of the Jacob stratification. And that allows us to finally prove the theorem.
Are we here? Is it stuck?
Κώστα. No.
Κράσανε μάλλον.
Mm.
Να κάνω pause το recording, τι να κάνω?
Ας περιμένουμε λίγο μέχρι να... Όχι.
Μπορώ να το κάνω pause.
Α.
So after unexpected technical trouble, we can finish the talk. So now that we have the Jacob stratification, we can prove the theorem we stated before, that this map is flat. In particular, using the Jacob stratification, we can show the Lafforgue variety is Cohen-Macaulay if the center is regular. Therefore, the result just follows from Hironaka's miracle flatness, as we saw last time. So we get that this is obviously regular. This we can show it's Cohen-Macaulay, so by miracle flatness, this is flat. And the dimensions of the fibers are correct. So if there are no questions, are there any questions until here before we move to an example?
Kostas, sorry, maybe you said it, but so what it means for the variety to be Cohen-Macaulay here?
So we just use the Jacob stratification. All this works fine in the case of a regular center. So for the case of regular center, the Jacob stratification just allows you, the fact that the strata are defined by the Jacob stratification allows you to show they are Cohen-Macaulay. For a non-regular center, then it's much harder to work with because you can take a regular subalgebra, but then you don't have any more. If you look at spec A being something honestly smaller than the center, then you can't make an argument like this anymore, that everything will be isomorphic to some yi. They will be contained in something like that, but they will not necessarily be isomorphic. So recall that the Cohen-Macaulay is a singularity condition. Essentially, it tells you your space is not very singular. And, well, the Jacob stratification gives you a kind of equations that always give you Cohen-Macaulay schemes.
Πάλι τον χάσαμε ή μόνο...
Έτσι φαίνεται, Μέρη.
Εγώ, οκ.
So, we have the result by Hironaka's miracle flatness. Let me finish with an example. What happens for the affine Hecke algebra of SL2 that we saw last time? Well, then this is the very concrete algebra generated over this ring by elements 1 and TS that satisfy these relations. We can just compute the discriminant here. We only have to compute the discriminant because we only have one reducibility locus. But if you're not convinced, you can just use the exact same calculation we saw last time, just for the case of parameter Q. So we can exactly compute the discriminant. And what does this tell us in this case? How do things look like? Well, generally, we saw last time, we saw the classification of modules, we expect the Lafforgue variety to look like this. So by Q, I mean the special, let me call it T. If I specialize Q to T, then we saw last time that in terms of modules, I get something like that. And this is reasonable to expect because how many zeros are here? Essentially 2, because we're looking at Lorentz invariant. So this is, we're looking at the invariant polynomial. So this gives a point and this gives another point in this T modest 2. But this is only true if T is not equal to 1. If T is equal to 1, then we'll only get 2 points and we'll basically get a double point. So if we look at the discriminant, it gives a double point. Why is that? Because now you can, what you do is you just look at the Lafforgue variety over the whole algebra, not just over the specializations. And what you will get is some shape like that. So I've put a new direction for the deformation of the parameter Q, which except the case of T being minus 1, it will give you 4 different points. But it generates for the case T equals to minus 1. And this is not a coincidence. That means this whole thing is flat when I project it to the parameter Q. But so computing everything, if this is where the parameter deforms over, what we'll get is something like that. So when we change Q, normally, except the case T equals minus 1, we will get 4 points, and at T equals minus 1, we just get 2. We can also see at this, our space is singular at this point, but it is still Cohen-Macaulay, of course. And so we see we have a flat deformation, whatever Q is in particular, over the whole spec of C Q plus or minus. In particular, it doesn't ruin flatness when we look at T equals minus 1. It's just we have a singularity, which is why we get less irreducible representations. So in this deformation theory, we don't need to look outside roots of unity. It's just that at roots of unity, the space becomes singular. So, and with that, let me only talk about the possible further generalizations. Can you all still hear me?
Yes.
Okay. So we can substitute, if you look at this proof, we can substitute any regular ring instead of deforming over just one parameter, and in particular, Lorentz polynomials over many variables. This appears in a lot of useful Hecke algebras coming from representations of p-adic reductive groups and the Langlands program. It should also be true that you can do the same thing for non-regular centers. It's just that the proof we have until now only works for the regular center case. But I have independent results in about centers that are non-regular. And the biggest dream would be that it works if Z is just Cohen-Macaulay. And we need to assume that if Z is not Cohen-Macaulay, miracle flatness works in both directions, as we saw last time. So if Z is not Cohen-Macaulay, there is no hope for flat deformation to work. It's not just that it's something that may be very hard to show. It will not work. But the biggest hope would be that we can show it for Z being just Cohen-Macaulay. And if we do that, this assumption in practice is always true. Like, it's very rare to see non-commutative algebras in practice that the centers are not Cohen-Macaulay. And here are the references. This is the paper where everything I've talked is about. 2 is where Lafforgue's statement was first, Lafforgue's proposal was written, and 3 is one of the papers that the conjecture was mentioned. Actually, the first one was in 2007, but in this one, more things are explained, which is why I decided to put this as a reference. If you want the 2007 reference, I can also send that to anybody that asks. Thank you all for listening, and sorry for the technical problems.
Ευχαριστούμε, Κώστα.
Εγώ ευχαριστώ και λυπάμαι για την ταλαιπωρία. Καταλαβαίνω ότι ήταν κάπως distracting όλο αυτό, but any questions?
Περιμένω πως κάποιος έχει μια πιο μαθηματική ερώτηση και μου, γιατί εγώ δεν έχω λίγο πιο πρακτικής φύσεως.
Έχει σταματήσει το recording?
Όχι, should I stop it?
Ναι, ναι.
No.
Το κλείνουμε στις ερωτήσεις.
Okay.
Γενικώς.